Welcome to the basic input-output lesson. Today we will cover quite a few things. We'll start with a recap of pure functions, then an introduction of what I/O actions are, how they work under the hood, and how to use them in practice. Then we will use these new concepts with the getChar, getLine, and putStringLine functions. We'll learn about how actions are also first-class values like functions, and how to compose these actions. Finally, we will simplify our syntax using the do block, and we'll learn about the main function. And at the end, we'll have a small syntax recap. Let's get started. So far, we've been working with pure functions. These functions have no side effects and take all their arguments as input and produce a value as an output that depends only on those arguments. What we mean by input and output is crucial here. A function's input can be only the values we provide as arguments, and its output is the value it returns. For example, the lame function takes a single numeric parameter and returns a value multiplied by 3. The output of this function depends exclusively on the value provided as input. So every time we apply this lame function to 4, we will get 12. Even if you don't explicitly show the input of max 6, for example, we know that because filter is partially applied, it takes a list of integers. I simplify the signature a bit. Same as before, the output depends exclusively on the value provided as input. So every time we apply this max6 function to the same list, we will get the same result. And of course, functions are carried. So if a function looks like it takes multiple arguments, it actually takes a single parameter and returns a function that takes another single parameter and so on until all parameters are applied and we get the final value. If we use the same parameters, we get the same result. And in every intermediate step, we also get the same intermediate result. All good so far. But what if we don't have the input yet? What if we want to make an interactive program, a website or a game? When we write our program, we have no idea what the user will do with it. We can't know in advance if a player in our game will move to the left or to the right, or if a user in our website will click on a specific button or not. Those are things that happen while running the program. So there's no way for the programmer to pass them as inputs of a function. I mean, we could, but imagine if we choose them beforehand. A game that always does the same and finishes the same way, without any way for the player to interact with it. That sounds more like a movie. Still not bad, until you realize that you can't even show the image on the screen because that will entail sending and receiving information from your computer screen while running the program. So if you run this quote-unquote game, you're basically using your computer as a very expensive heater. The only way to provide our program with the information and capabilities it needs is to give it a method to interact with the real world. And for that, Haskell uses I/O actions. Before starting with I/O actions, I addressed the elephant in the room. I just told you that everything we coded so far was pure and that we couldn't interact with it. But we've been interacting with our functions and passing arguments since the lesson 1. That's because we've been cheating by using GHCI. GHCI performs I/O actions in the background without explicitly telling us. So at the end of the day, if we want our program to interact with the real world, we still need I/O actions. The name I/O action gives room for misinterpretation. When we talk about I/O actions, we are not talking about the input and output of a function. We talk about the input and output between our program and the real world. I/O actions can interact with and change the world outside our program. They might or might not interact with the world, but they can. That's the key. They are allowed to interact with the world, unlike pure functions. These I/O actions are what we call a side effect. A side effect is any observable effect other than the effect of returning a value. That's why all the functions we've written so far have been pure. The only thing they did was to return a value. It might sound a bit abstract. Let's see a few examples so we can build up our intuition. One possible I/O action is the one needed to obtain the result of what a person typed on the keyboard. In this case, the I/O action is interacting with the keyboard, and the result of this I/O action is whatever the user typed. Notice that I/O actions are on top of the diagram. We represented functions with boxes that took their inputs from the left and returned the outputs on the right. But now that we are dealing with actions, we indicate the side effects at the top of the diagram with arrows going both in and out, because side effects can both send and receive information. Another example is to show some text, an image, or something on the screen. In this case, the I/O action is to show something on the screen, and we don't get actually anything valuable as a result of this I/O action. And one more, a call to an API or a database. Doesn't really matter what you're actually doing with the API or database, but it's outside of your program, so you need an I/O action. In this case, the I/O action is a call to the API or the database, and the result is some information you asked for. Okay, so we are clear about the idea of I/O actions. But how does Haskell handle those I/O actions? Now I'm going to show you the definition of the type that allows us to safely interact with the real world using I/O actions. A heads up, don't try to understand the code. We will only use it to create a mental model of what's happening under the hood. Without further ado, here's the I/O type. The I/O type constructor has a single I/O value constructor. The interesting part is the function passed as a parameter of the value constructor. It takes the state of the whole real world, does something to it, and returns a tuple containing the new state of the real world and a value of type A that was generated while all that was happening. Aren't the designers of Haskell a bunch of smarty pants? If you give a function the state of the whole real world, that function can do anything. Talk to databases, access files on your computer, allow penguins to fly, anything. We use it to print stuff on the screen though. Of course, this is not what is really happening under this seemingly magical type. But we can think of it this way. The I/O type is actually an abstract type. An abstract type is a type whose representation is hidden but provides associated operations to work with it. So the inner workings of I/O are hidden to us, and instead we get a bunch of functions and actions that use this type, which means we don't use the I/O constructor directly. We use functions and actions that operate with I/O values. So there you go. That's as far as we are going to go about this. If you want to know more, there are tons of tutorials out there, or you could even explore the source code yourself. but I would recommend waiting until you are more fluent in Haskell to tackle that challenge. Now let's switch to the practical side. In practice, we don't really care about the details of how the interaction with the real world is handled. We don't even care about how the IO type is defined. The only thing we care about is that if we use it properly, the compiler will handle the details, and we won't get any surprises when running our code. So let's learn how to properly use the IO type. Let's look at another diagram. The IOA type tells us that something is an IO action that first interacts with the real world and then returns a value of type A. For example, this action 1 of type IOBool performs an IO action and returns a boolean after it performs that action. Same with int, same with this function. In this case, the IO action is performed and after that it returns a function. And finally, this IO action that returns what looks like an empty tuple. There are three things to note here. One is that after performing the action, we get a value of the specified type we can use in our code. The other is that the action returns the value after performing the IO action. We cannot get the value without performing the action. And finally, we see a new type in the last action, the unit type. This is the unit type. We see that it has only one value constructor that takes no parameters, also called nullary constructor. So it's a type that has one possible value, this one. Also, notice that the type and the value have the same name.
But wait, why do we learn about this just now?
Well, because until now, we've been working with pure functions. If the only thing a pure function does is to return the unit, why do you even bother using that function? Just use the value directly. And if a function takes the unit value as a parameter, why do you even bother requiring it if it's always the same value? Just remove that part and use the unit inside the function directly. So when you think about it, we could remove the unit type for any pure function and lose nothing. But now that we are dealing with actions and side effects, there are plenty of cases when we don't really care about what the action returns as a value, because we care only about the side effect it performs. Take printing something on the screen or deleting a file. We don't need something in return. We care only about the side effect. That's why now it makes sense to have this type, to represent a value that we don't care about. If it doesn't quite click, don't worry, we'll see a couple of real-life examples right now. The most basic IO action I can think of is getChar. This function performs the IO action of asking the user to write a single character on the standard input. As soon as the user writes that character, it takes it and finishes the IO action. The value of type char it returns is the character the user wrote. We can run the function to see how that works. Just now we perform the IO action. This action is still running because it's waiting for the user to get an input. So we will get the input, okay. When we hit enter, the IO action finishes and returns the value k as the result. As you can see, when we run this cell, a text area appears so we can input a character. There's still some magic going on because we are using the Jupyter cells that run GHC under the hood, but we will get rid of this soon enough. Now, there are cases when a single character is enough, like when you need to confirm or deny an action in a command line interface. But what about a whole phrase? For that, we can use another function called getLine. This one performs the I/O action of asking the user to write a line on the standard input. And the value of type string it returns is the text that the user wrote until it pressed enter. So if we run this cell, we can say, hey, from the outside world. And that string of text was returned as a value inside our program. The getChar and getLine functions aren't great and all, but if we run a program with just this, it will prompt us for a character or a string without any explanation. Like when your dog suddenly stands in front of you and silently but intensely stares at you with puppy eyes. You know it wants something, but what? Not only do we need to get, but also send messages to the outside world. And for that, we use the putStringLine. PutStringLine is a function that takes a string as an input and returns an I/O action. And what does that I/O action do? Prints the string we previously passed as parameter to the standard output. For example, in this line of code, putStringLine is applied to the string hello world from inside the program. When we run this action, we will produce the side effect of printing this string to the standard output, like this. Again, this seems like any other function that returns a string because we are using a Jupyter cell that prints the output of the functions. But this time, we are actually performing the I/O action ourselves. But check this out. If we run this last cell, we don't get the string in our standard output. That's because we didn't ask for the action to be performed. We just named it X, and that's it. We never actually needed the action to be performed, so Haskell didn't perform it. And that's another property of actions. They are what in programming are called first-class values. It just means that you can treat actions the same as any other value. For example, the putStringLine is actually an example of a function that returns an action. We can also bind action to names. We can put them inside the list of other data structures, and we can pass them as function parameters. If we run this, everything's okay. And if we run the fake length function passing the list of action parameters, we don't get any of the messages in the standard output. Even though we are evaluating a list that contains actions, we don't get any of the messages in the standard output because none of the actions inside the list are performed. Why should they be performed? We just ask about the length of the list, not the values it contains. Remember that Haskell is lazier than a cat sunbathing. It won't do anything unless it has to. So, until they are performed, I/O actions are just plans to do something, programs to be run, or actions to be performed. And because these side effects aren't performed while evaluating all those expressions, we can keep reasoning about our code the same way we used to, and only care for the actual side effects when we ask Haskell to perform them. So, how can we ask Haskell to perform a few different actions? We can start by composing them with special operators. we will create a few simple bots to learn how to compose I/O actions. The first one is a root bot. As soon as you interact with it, it yells at you. It starts with a simple message. As soon as you run this action, you get the "Hey" message in your standard output. The bot has to catch its breath before yelling at you again. So we will add the next phrase in a second action. To do that, we'll introduce the then operator. This is actually an overloaded operator, but we will use a specialized signature specifically for I/O actions. And as you can see, the operator takes two actions as input, I/O of A and I/O of B. It first executes I/O A, ignores the result, whatever A is, and returns the I/O B. If this were a pure operator, the implementation would look a bit like this. A pure then that takes two values and returns a value of the same type as the second, and when we see the implementation, we see that it takes the first value x and the second value is y, ignores the first value and returns y. That's it. So 3 pure then 5 is just 5, and if we compose a bunch of functions, we see that the first value will always be ignored until we get to the last one and it returns the last one. So if then was pure, we will be just throwing away the first value and returning the second. That's it. But because we are dealing with I/O actions, this operator has some secret sauce that allows it to perform the first I/O action before returning the second one. More specifically, the then operator sequentially composes two actions discarding any value produced by the first. For example, ABC is an action composed by multiple actions. When we ask Haskell to perform the ABC action, it first performs the putStringLine A action and discards the result. Then it performs the putStringLine B and discards the result. And finally performs putStringLine C and returns whatever the last action returns. So, because putStringLine C returns the unit after the side effects, the ABC action returns the unit after the side effects. Notice that the direction of the arrows indicates the direction of the sequence. We perform the actions from left to right. Now let's use this operator to finish our root bot. As you can see, we're using the then operator here. So our root bot will first perform this action and print hey to the standard output, and then perform this action and will yell, "Get out of my lawn!" Exactly what we wanted. But maybe we could make it even ruder. How could we make this bot even more annoying? I know. Let's make it seem interested and then yell at us. So it also wastes our time. We'll make the bot ask our name, completely ignore it, and then yell at us. All that with this simple code. It's getting a bit too long, so we'll split it into several lines. Besides that, not much has changed. The only real change is that we added the getLine function in between the putStringLine ones. But if we run it now, we see that first it performs the side effect of asking our name in the standard output. Then it performs the side effect of waiting for us to type and returns that as a value. But because we are using the then operator, we ignore it, and finally it sends the last message, like I care. It's definitely ruder than before. But maybe we took it too far. Let's learn how to use the value returned by getLine by taking our bot to therapy. After therapy, our bot feels way better and wants to be our friend. And for that, it has to use our name. We cannot use the then operator because that ignores it. So we need another operator that does the same but passes the result of the first action to the second one. And that's the bind operator. This is also the specialized signature for IO actions. It looks complicated, but it's not that different from the then operator. This operator takes an IOA action and a function that takes the value of the same type A as the one produced by the first action and returns the action B. What this operator does is it performs the IO action to get the value A. Then it passes that value to the function to get the value IOB and returns that as a result. The operator does not perform the IOB action, just the IOA. So, the bind operator sequentially composes two actions, passing any value produced by the first as an argument to the second. For example, here we have two functions, the yellit function that takes a string and returns an IO of unit, and we can see that it prints to the standard output whatever string it takes concatenated by a bunch of exclamation marks. And here we have the yellit back IO action that returns the unit, and we can see that it first runs the getLine action to get a string, and then it passes the result as an input of the yellit function. So if we run the yellit function, we see that it prints the same string but with exclamation marks. But if we comment this and use the yellit back function, we see that it prints whatever we send through the standard input to the standard output with that extra modification. And that's pretty much it. Now let's use this operator on the now nicer bot. We create the bot after therapy function that first asks for a name. Then it waits for you to provide it, and after you do, it passes that value to the respond function that uses it to print a message. Let's quickly use it. Perfect. It works. But the response function is a simple function that we only use once. And we already know what to do in these cases. We use a lambda function. The only thing that changed is that now the body of response is inside a lambda function that takes as a parameter whatever getLine gives back. And if we run it, of course, we get the same. And there you go, a simple and compact function with just a little bit of noise. Our bot is now completely rehabilitated, and it turns out it's a chatty bot. Let's add a few chatty features. For example, let's add another message that tells us the number of letters in our name. The letters in name function is a pure function that takes a name and returns a silly little comment on it. To add it to our chatty bot, we need to do it like this. Here is the new part. We need the value name. This value is provided as the result of the second action. So we need to compose our action inside the lambda function so we have access to this name variable. That's why we have to put it here and not here. And now we can run it, this one, and then this one. And there you go. And from now on, it's more of the same. We can keep adding more and more actions in the same way. Here's something a bit more complicated. This is our final chatbot. It's an IO action that returns the unit. This IO action is composed by a bunch of actions. The first one is to print something on the screen, then get a string from the user and pass this string to a lambda function that assigns this string to the variable name. And this lambda function first prints a string using this name, then prints another string, but this time we pass the name to the letters in name function, this pure function that takes a string and returns a string. Then we use the name again to ask another question, what do you do for fun? Wait for another response. We take the result of that response and pass it to a new lambda function, and we name the result of getLine hobby. And inside the body of this lambda function, we print another string, but this time the string uses both the name and hobby variables. Let's see how it works. Hey, what's your name? Robertino. Nice to meet you, Robertino. Your name has 10 letters in case you were wondering. So, Robertino, what do you do for fun? And it crashed, of course. It seems like there's a bug in the Jupyter's kernel implementation, but we don't really need this anymore. We can just copy this, move to a different tab, go to the Haskell course repo, wait for a bit. We have our development environment ready, so let's close all this, create a new file. Let's see, this is a bit too big. Let's create a new file. IO lesson bug.hs. Perfect. Oh, no, we don't need this server right now. Let's move this bit. Perfect. So now we can paste our function. And if we will try to load this in GHCI, load IO lesson, we will get that there's an error because we didn't copy and paste the letters in name function. So let's do that. Let's make it a bit smaller so we can see the whole code. Perfect. This is the whole code, yes. Perfect. Let's save. And now reload the file. And it compiles, so it works. Now if we run our final chatbot. Hey, what's your name? Robertino. In case you were wondering, so what do you for fun? And now the second getLine function runs and waits for me to respond. So let's say coding. Are you kidding? I love coding. As you can see, the last one uses both Robertino and coding, the two variables we passed in the getLine functions, and it works as expected. Although, as you can see, if we keep increasing the actions, we start to see a pattern, and ugly and hard to read pattern. Luckily, we have a sweeter alternative, the do notation. The do notation is just syntactic sugar for expressions composed by the then and bind operators. We are going to rewrite all the previous expressions with do notation so we can see the difference, starting with a root bot. As you can see, we write the keyword do after the equal sign, and then we start a block with the actions. In this case, this syntax is not very useful. It's more straightforward to write it without the do syntax. Let's see the second version of rootbot. Now we start to see some slight improvement. It's not much, but we can see that each action is in a different line, making it easier to identify. Without the do notation, the actions go from left to right. With the do notation, they go from top to bottom. And what about the even ruder bot? Same as before, we add the do keyword after the equal sign, remove all the thens operators, and you are ready to go. Notice that we align everything at the same indentation level. Now is when the cool stuff starts. Here we have a root bot after therapy. How do we handle the name here? In the previous bot, we ignored it, but now we need a way to bind the result of getLine to a name. For that, we introduce the left arrow binding. This left arrow binds the result of running the getLine action to name. And once you have the name variable, you can use it anywhere after that action. Notice that because the type of getLine is IO of string, our name will be of type string. Now let's see how we can use do notation for the chatty bot. Now the differences start to get big. You have to stop on the chatbot function for a few seconds to grasp what's going on. But chatbot do, it's really easy to follow. It first prints something to the standard output, then gets something from the standard input and saves it in the name variable. And then it prints another message using the name and another message passing the name to a function. Perfect. Finally, let's compare the most complicated one. I'm going to highlight final chatbot so it's easier to separate both. As you can see, it's really easy to follow here. We don't even need to go through it line by line. But notice that you have to always keep all the statements aligned at the same indentation level to avoid confusing the compiler and having silly errors. As you can see, the do notation is nice to read and write. It allows us for a more clean and concise code. But wait a minute, this code looks oddly imperative. We are stating what to do step by step in sequence. Wasn't it that declarative code was so great? Well, until now, all the functions we wrote were pure, which means that we will always have the same result no matter the order of evaluation. That's why we could write declarations and let the compiler handle the details. Now that we have side effects, the order in which things happen matters. We don't want to run the side effect of getting the name before the one that prints "What's your name?" That's why we adopt a more imperative style with the do notation. And that's the do notation in essence. Although there are a few other things regarding the practical aspect of using do notation. It gets a bit more complicated, but not too much. Let's start with how to use let inside the do notation. We can use the let keyword inside the do block like this. Here we have the unscramble IO action that first prints a string to the standard output that says write a bunch of numbers and letters scrambled together, and then waits for the user to actually do it and saves the result of that action in the arg variable. Then we create two let bindings. The numbers binding is a value obtained by filtering all the elements that are numbers from the argument. And the letters binding is obtained by filtering all the elements that are not the numbers obtained in the previous let binding of the argument. That way, we take the original string and get only the numbers, and we take again the original string and get only the letters. And then we just print the numbers are these ones and the letters are these ones. Let's run it. As you can see, it works perfectly. There are a few details to keep in mind. The constructs bounded with the let keyword are lazy. So even though they occupy a line in the do block, they aren't evaluated unless needed somewhere else, like here and here. Also, we don't need the in keyword like we do outside the do notation. Everything after the let binding can access it. Same as the variables bounded using the left arrow. And finally, if you have a couple of let bindings, one after the other, like here, the let keyword is needed only for the first one, as long as you maintain all bindings at the same indentation level. So as you can see, numbers and letters are both at the same indentation level. It is not mandatory to use this feature. You can just write let here and it's the same, but it's convenient. The let binding syntax is pretty convenient overall. Same as the ability to nest do blocks. We can nest do blocks as much as we want. For example, this plus a decade action first asks the age of the user. Then it checks that the string provided contains only numbers. We use the same filtering method as before. The difference is that instead of filtering, we are just checking that all the elements in the string are also present in this string. So this should return true if all the elements in the age string are actually numbers. Else it will return false. Now that we have this boolean, we can check if validation is true, then do. As you can see here, we are using a do inside another do block. And here we use the read function, that is the inverse of the show function. And we pass this string saying that is of type int. So if this string can be parsed to a number, we get the age, but now as an integer. That's why we needed to make sure age string was a number before doing this conversion. And now that we have the age in numeric type, we can do math with it. So we add 10 to the age and print the message, in 10 years you will be this much years old. If age string doesn't contain only numbers, this will return false and we will have landed in this block. Another do block that instead prints your age should contain only digits from 0 to 9. Alternatively, press Ctrl C to close the program. Why do we tell the user that they could print Ctrl C to close the program? Because we are passing plus a decade, the same function we are creating, recursively. This means that if the age is not valid, we will print a message and run this function again. So the user will have to rewrite their age again and again and again until it's only numbers or it presses Ctrl C. Let's run it. What's your age? I say, who are you? And doing in my house. As you can see, we didn't provide a valid number, so we enter the else clause, print this message, hey, your age should only contain numbers, and we ask again, we rerun the plus decade. Now we provide a valid number, 30. In 10 years, you will be 40 years old. An important detail is that the last element in a do block has to be an expression that returns an IO action of the correct type. If we look at how the plus a decade function ends, we have two possible cases depending if valid age is true or false. Inside the then, we see a do block that ends with put string line applied to a string. So the expression is of type IO unit, like we indicate in the plus a decade signature. All good. Inside the else clause, we have a do block that ends with a recursive call of the plus a decade function, so is of type IO unit. Also all good. Of course, we couldn't have ended with something that returns a value of type IO int or IO bool. But there's more. We cannot do something like this. Here we have the twice function of type IO string. This function starts with a do block that first gets something from the standard input of type string, and then we say, okay, let this TW variable equals to this string twice. This produces an error. Why? Let's take a look at the code without all the sugary syntax. If we take a peek under the hood, we see that the let binding expands to a complete let expression, and the problem is evident. It's an incomplete expression. Let TW in what? And that's when the brilliant idea that we all have when first learning Haskell comes to mind. What if I return the string like this? The only thing we say, okay, let TW in TW, so we just return whatever we created. The let expression is complete. But now we have a type error because we have to return an IO string and we are returning a pure string. Easy fix, we can change the type of twice to string since that's what we are returning. And just for completeness, here's the equivalent code with do notation. If we try to compile any of the last two versions of twice, we will also get a type error. But we said that the type is string, and we are returning a string. What's the problem? The problem is that we used the getLine impure action inside twice, and we are trying to return a pure value. In Haskell, once you go impure, you cannot go back. There's no redemption. In other words, you can't escape IO. Let's talk about I/O and the return function. Just to make sure there's no confusion, return does not work like in other programming languages. It's a different thing. If you don't know any programming languages, don't worry about it. I wanted to open with that just to avoid confusion or in case you were about to skip this section. Okay, so let's go back to the problem at hand. Why doesn't this code compile? Well, because if we allow that to compile, for the one that uses the twice function, it would look like it's using a pure function. Pure and impure code will be able to mix together. And if that's the case, we would never be sure if our code is pure, which means that we would never know if our functions behave like we think they do. We will have to treat everything as if it was impure, and we would lose all the advantages of purity. No more referential transparency, no more code that's easier to reason about, no more certainty that modifying a function doesn't break anything without you knowing about it, etc. That's why we cannot return a pure value if we perform an impure action inside the function. There has to be a way for both the compiler and the developer to identify if we use an impure action. The solution is simple. Once we use any side effect, we will never be able to escape impurity. How does this work in practice? Well, we can perform I/O actions to get the resulting value and work with it, like we did with getLine to obtain str, as long as we do it inside another I/O context. The compiler enforces this by checking that a function performing an I/O action inside has to return an I/O action. So, because we perform the getLine action inside twice, now twice has to return an I/O action. The compiler wants us to return an I/O action, but I want to return TW, and TW is a pure string. What can we do now? That's when the return function comes in handy. The return function injects a value inside an I/O action that does nothing. It takes a value of any type and returns an action that results in that value. Remember when we presented the idea of I/O actions that we say that they may interact with the real world? Well, in this case, it doesn't. The action returned by the return function is a dummy action that doesn't produce any side effects and returns the value. This is perfect for our use case. We need a value wrapped in an I/O action, but we don't really need to perform any more actions. So, using our new function, we obtain the final version of twice, which without sugar looks like this. As you can see, the only thing we needed to do is to pass the value we want to return to the return function. And because this function returns an IOA of the same type as the value passed, we return an IO string. And that's why twice is of type IO string. And here, without the do notation, we do the same. Let TW in return TW. So TW is passed to the return function that takes a string, so it returns an IO of string. And that's why twice is of type IO string. Remember that return is just a function. It doesn't need to be used at the end, and you could use it multiple times like any other function. And that's pretty much how we work with side effects. You might be thinking, but if once we use an impure action, we have to carry out that IO type forever, where does it end? And if we need to interact with the world at the beginning of our program, like when a user clicks on the start button, doesn't that mean that the whole program now will be impure? Those are valid questions. Let's answer them one at a time. Like many other programming languages, Haskell has what is known as an entry point. The entry point is the place in a program where its execution begins. The first thing that runs when you run the program. Many programming languages have entry points, and in almost all cases, the entry point is named main. Sometimes it's a function, others is a static method. Rust, Java, Dart, C, C++, and many more have it. And of course, Haskell has it. In Haskell's case, it's an I/O action called main. This action is the only one that gets executed when we run a program written in Haskell. And it always has the type I/O unit. Actually, you could return a value different than unit, but it will get ignored because there's nothing above this action, so there's no point. Now, when you interact with the outside world and have to carry out the I/O type, here's where it ends, in the main action. An important thing to know is that if you want a function or action to be evaluated and performed when running your program, it has to be directly or indirectly inside main. When composing actions and functions, in the end, we are gluing everything together in a single I/O unit action that, when run, performs everything as we specified. Why do we hear about this just now? Because we have been using GHCI that handles all this behind the scenes. But in the next lesson, we'll start working with real compiled programs, so we better start practicing now. On that note, let me present you one of the shortest programs you could write in Haskell. This is it, a complete Haskell program. You could put this in a Haskell file, compile it using GHC in the file name, and you will get back a program that runs Hello World when executed. Okay, so if every time you perform an action, you have to carry the I/O, and the first thing a Haskell program runs is an action that has all the code inside, at which moment do we write pure code? Haskell programs in the real world usually have a small main action with a couple of actions and a couple of pure functions. And inside those pure functions is where the bulk of the code lives. That way, you minimize the interaction with side effects, and most of your code is pure and easy to deal with. Sort of like this. This is a complete program that first uses an I/O action to get some configuration. This could be from a server, from your local computer. It doesn't matter. We just perform an I/O action to get this config file in a pure form. We pass this configuration to a pure function to get the result, and then we perform another I/O action to print the result. The bulk of the code is pure and is inside the pure function that takes a pure config value. And a small part of the program interacts with the real world to get the configuration and to show the final result. And that's pretty much everything I wanted to cover for this lesson. It's a lot to take in, I know, but with everything we covered today and a little practice, you will have no issues writing interactive programs. And because I know we covered a lot of new concepts and syntax, here's a recap to use as a refresher while working on the homework. Pure always produces the same result when given the same parameters. Impure may produce different results for the same parameters. Pure never has side effects, impure does. Pure never alters the state of your computer, of your program, of a global variable, or whatever. And impure may do alter the global state of the program, system, or world. Pure doesn't have I/O, impure does. Pure functions behave nicely, and you have to be extra careful with impure actions. And as a small syntax recap, this function is used to sequentially compose two actions, discarding any value produced by the first. This function to sequentially compose two actions, forwarding the value produced by the first to the second. This function is used to inject a value inside a context. The do keyword is used to start a do block. The left arrow inside a do block is used to bind the result of performing an action. The let inside the do block is a lazy binding of any expression. It doesn't perform any actions. And finally, the main action is the entry point of a Haskell program. All functions and actions have to, one way or another, end in main if you want them to be performed. And that's it for today. If you are curious about how to create your own programs, don't worry. Next lesson, we'll learn how to set up your own local development environment, how to use modules, and how to manage Haskell projects. We'll still provide everything in online Jupyter notebooks and online development environments, but we'll remove all training wheels so you can manage your own project by yourself if you want to. Make sure to complete your homework, and I will see you in the next one.